But I'll just start with some comments. So I've talked to some random people, and seems like about half of the people I talked to actually downloaded did the homework, which is to download one of these codes, install them, hello world, and also to just go to dcp.stanford.edu to play with it. So, which you can do. That's what you have laptops for. So, have you done it? You did. Yeah, did you install one of these things? Did you install one of these codes? Like CVX, CVXPy, or convex.jl? Oh, you use it already. Okay, so then you don't count. Okay, good. We'll leave it that way. All right. Anyway, if you haven't, this is actually how you learn a lot about these things. So, okay. So today's lecture is actually just, it's a set of applications. They're essentially not connected, with the exception of maybe the first two. And what we're going to do in these applications, actually, let me tell you what the theme is. In the first lecture, we talked abstractly about different things you would use optimization for, like worst case analysis, model fitting, or designing some kind of optimal action. And so what we're going to do now is we're going to actually go into a couple of application areas with a little more detail. Instead of 2 slides, we're going to have 8 or 10. The fact is, actually, some of these things you're going to get to near the forefront of knowledge. There'll be a lot of other stuff behind it, but you're going to actually learn a lot about how some of these things work. I can skip them, move them. We'll see how the timing is going, stuff like that. And let me tell you what the big takeaway message from today is this. There's a lot more you can do with optimization than just than just fit models, which is, I suppose, what most people here do. Okay, you can do a lot more. And once you're trained in these areas, you can apply these ideas creatively to just tons of application fields, right? So, I mean, of course, if you want to continue just minimizing a loss plus a regularizer, please go right ahead. But at least in that case, you should know that these ideas apply across many, many other fields, right? So, okay. So the first thing the first little mini topic, in fact, if you don't know anything about it, you're going to end up knowing quite a lot in about 15 minutes. Actually more probably than a lot of people who actually do it. So we're going to do portfolio optimization. And the examples are chosen to kind of illustrate some of these different categories, right? So, so we'll start with the basics. So we're going to work with the fractions. Right, so we have a vector W in Rn, and it's the fractional asset allocation, right? So these are numbers that add up to 1. If they're non-negative, that means that's, of course, a convex combination, right? But we can have negative things here, right? And so when you have a negative allocation, it means you own some negative value of shares, and that's basically having a short position, right? So a short position means you borrow shares and you actually have the obligation to return them later, right? So, which by the way turns out to be mathematically and in every other way exactly equivalent to owning a negative number of shares. So I don't know if people have seen this before. If you haven't, it's just kind of cool to know about, okay? So, okay. This is going to be the portfolio allocation vector. It's going to satisfy this. It adds up to 1. And if this vector is non-negative, it's called a long-only portfolio, right? So it's called, if you own a positive, it means you've taken, or in the dialect of finance, that means you've taken the long position if you own the shares, right? So if you actually have an obligation to return shares later, that means you've taken the short position, right? So, okay. Now there's an idea of leverage. Leverage tells you, how much you've actually borrowed or shorted, and then you turn around and use that to put that into to buy other assets. And unfortunately, people in finance are completely inconsistent in how they define leverage, including like the same person on different days. We'll use different ways to describe it, right? So one that comes up frequently, but I don't even know if it's the most. So after a while, I gave up. But what I've learned now is when you talk to someone in finance and they say leverage, you better ask them, what do you mean, right? So This is one that's used pretty widely. It's the one norm of W. Now, if W is a non-negative vector, obviously that's 1, right? Because that's the positive part of W. That's actually all of W's. That's 1 here. Otherwise, for example, if the leverage were 2 to 1, then that would have a meaning. It would mean basically that you have, it would be that on the long positions you'd have a total of 2, I guess something like that. Let's see, 2 to 1 would be whatever it is. Anyway, so it means you've borrowed an equal amount and then you've gone, you've used that to go into long positions. Okay, so this is leverage. Okay. So how do asset returns work? Well, you're going to hold these investments for one period, right? You can also look at multi-period things, but we're going to start with a simple thing. You're going to hold investments for one period, and you start with some initial positive prices. That's PI. That's for the different assets. And then at the end of period prices, you're going to have PI plus, right? And by the way, a period could be a day, a week, a month, a quarter, an hour, a minute, or a second, or 10 milliseconds, right? So none of this matters to what we're doing here, okay? So you have initial prices, and then the final prices, and if this is bigger than this, it means that the price went up, and if you had invested some fraction of your shares in it, then you would have done well in that one. If it goes down, and WI is positive, you'll have done well. So the fractional returns it's the fractional increase in price. So if this is negative, then that means that that asset went down in value, okay? And had you invested in it, you would have lost, right? If you had gone short on it, you would have won, okay? So I mean, these are all kind of obvious things. Mostly, this is just setting the dialect, explaining what the dialect is. Actually, what I like to say is we refer to there's dialects, right? And yes, machine learning has one, by the way. So a very strong accent, I might add. I understand most of it. But, you know, statistics has one. Electrical engineering is terrible. So signal processing has a very strong dialect. Control is hopeless. Image processing, they're okay. Statistics, again, hopeless. So there's all these different dialects. And then we refer to high BBC mathematics. That's the standard language that theoretically all of us can. So if you're talking to someone and they're speaking a different dialect, and they say, oh, well, you know, all you need is your, you know, we have to talk about the risk and the leverage and the blah, 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 and such an option or whatever. And then you say, I have no idea what you're talking about. Theoretically, you can back off to high BBC mathematics, which hopefully anybody can understand. Okay, so, okay, back to this. So the fractional return on your portfolio is simply R transpose W, right? So this is the idea, right? So, and you know, this is kind of obvious, but if an asset goes up, that means that Ri is positive. You want this to be big, then it means you'd like Wi to be positive there, right? And if Ri is negative, you would like Wi to be negative. So you'd like, I mean, this would be the ideal, right? Okay. Now, common model is that R is a random variable, the returns, with a mean mu and a covariance sigma, right? So that's a very common model of this. It is, in fact, false, just for the record. So as pretty much anytime anyone says, I'm modeling this as a random variable, that statement is false, right? So it's useful only to the extent that when you pretend it's true, carry out methods, you actually end up doing something good in the end, right? So it's false here, but I mean, what it's really, I mean, it's an economic system. It's a social economic, it depends on who's doing what, all sorts of sleazy things happening, illegal, some legal sleazy things, illegal sleazy things, people have insider information, all sorts of crazy stuff is happening. And we'll just call it a random, I mean, the standard model is to pretend it's a random variable. Okay. Okay. And that means, of course, that your return is a random variable, right? And so when you choose, I should say, sometimes there's one asset which is cash, and that people pretend that has zero, that has like a fixed return, which is the interest rate. That's sometimes called, I don't know, the risk-free interest rate. And then that one would actually, there'd be a row and column of sigma that's zero, and that means that really is risk-free, okay? So, okay. So this is a random variable, and it's got a mean, mu transpose W, and it's got a variance like this. And so this is simply expected value bar. That's the mean return of the portfolio, but people just say it's the return of the portfolio, right? And sometimes they talk about the realized return of the portfolio because after the fact, you'd say, well, before you go into it and you don't know what R is, you'd say, well, my expected value is 5%, right? And then you'd say, well, what did you actually realize? And you go, oh, it was a good day, I got 6, okay? Something like that. That'd be the realized one. Okay, and then variance is simply called the risk, although again, people say the variance is the risk, but then half the time when they plot it or say what it is, they give it as the square root of that, right? So again, people are not consistent about what risk is. By the way, also, I'm going to show you the most basic ones. There are actually extensions of these where they have things like downside risk. Right? If you think about this, it's a bit silly because if your expected return is 5% and the realized return is 8%, that's good. That's not bad. That's really good. And so then there's a version where you only look at the variance of the downside. I mean, so there's all these. I'm not going to go into that. This is the most traditional one, right? So this would be variance is risk. Okay. And there are two objectives in choosing W. Here, you have to choose these weights. They have to add up to 1. Two objectives. One is you want high return. You want this thing large. And you want low risk, right? So these are this is just completely classic. Oh, and if you want to know the year for this is we're at 1953 right now. Just if you want to know where we are, right? So, so this is classical. This is 1953 portfolio optimization. And it looks like this. It says what you're going to do is you have two objectives, and to handle that, you're actually going to make a weighted combination, and you're going to fiddle with the weight, and that's going to trace out the Pareto curve, the optimal trade-off between the two things, right? And so, and I'm doing this in the way they talk about it, okay? So that's this. This is, you maximize the return, but then you subtract the risk because you want this to be small, and gamma, that's called the risk aversion parameter. And it's got some really sick units, I think, because it's weird to interpret because that's a quadratic and that's linear, but anyway, okay. So this is called the risk-adjusted return, right? So it all makes like perfect sense. And mostly I'm just filling up your symbol table so that if you meet someone who does finance, you will be able to speak to them, actually. So, okay. You have this constraint, of course, and then you have an additional constraint where this says that the portfolio you select, the allocation, has to satisfy various constraints, and we'll just call that a set script W, okay? So a common case is that you say that these things, every one of these W's has to be non-negative. That's called a long-only, and that's called long-only, portfolio or something like that. So this is the idea. And if you vary gamma here, you're going to get the optimal risk-return trade-off. And there's many variations on this, right? You can fix the return. You can say mu transpose W equals R required, and then minimize risk. You could put a risk limit and then maximize the return. You'd get the same trade-off curve. It wouldn't make any difference. So, okay. All right, so this is a typical thing. So this is, I guess there's 10 assets here. And then they're shown, this is kind of a standard plot where you show risk and return. Right? And so here are 10 assets. Let's see, we can look at one. Here's one that has a very high return and medium risk. Here are various other ones like this. I mean, what this of course doesn't tell you is the covariance, right? So you don't know you can't see the covariance behind this, but these are the diagonals in the covariance matrix, right? And then this green curve here shows you the optimal risk-return trade-off, right? And the first thing you see, I should say, on this plot, good is up, because that's high return, and left, which is low risk. Okay, so that's good. So good is up and left. And what you see is here's the optimal trade-off curve. And I mean, you get things like, this is long only, and you get things, these are for different risk aversion parameters. If it's very risk averse, that's gamma, large, or whatever that means, then you get something which is here. And actually, one thing you notice immediately is that these portfolios are all better than any of your assets, right? And this is, it should be obvious why this is the case, right? I mean, because I mean, you're exploiting all the covariances and things like that to do this, right? So, I mean, this is obvious, but this is exactly the kind of thing, if you showed someone in finance this, they'd know exactly what this plot was. Okay. And here, this is silly, but here are 2 points with two levels of risk aversion. One has, you know, a standard deviation of 0.6. It really doesn't matter what the units are, and a return of whatever that is, 1.3. And here's one with a higher return and higher risk, right? And so those might have return distributions that would look like that. And then you'd see that for the more risk-averse selection, there would be almost zero probability of a loss, right? Because zero would be, if you're negative, that's a loss. And this one would have a higher return. I mean, you've got good chance of doing quite well, and you have a probability down here, I don't know what it is, but it's a not zero probability or not insignificant probability of a loss. Okay, so this is all very slow, but this is just bringing you up to speed. Okay, portfolio constraints can look like this. Well, you can have none, right? In which case it's stupid because you're minimizing a quadratic subject to equality constraints that has an analytical solution. And in fact, the risk-return thing is a line, and there's a whole theory around that. That's called, I forget what it's called. It's like capital asset price, you know, CAP-M. They make a big deal about that. It's taught in business schools, right? So, okay. You could have a leverage limit, right? So you could limit the maximum leverage. Here's one that's not uncommon, is you'd say, I want my portfolio to be market neutral. So what that means is, so I should say what the market portfolio is, right? If I have a vector M, which is the vector of the market total capitalizations of all the assets, then M transpose, then basically M, if you take M transpose sigma W, that's the covariance between the market return and your actual portfolio return, right? And so if you make that zero, that means you don't have to worry about what the market did that day, right? You have a question?
Yeah, for those of us who don't speak finance, would you perhaps
Hey,
explain what capitalization is?
careful here. What's that? Oh, sorry. Okay, fine. I was going to say this is pretty much high BBC mathematics, but okay, fine. What is capitalization? It's that if you have a company, they issue stock, and it's the total value of the company. You take the number of outstanding shares, you multiply by the price of the share. That's the capitalization. That's a good question. Good.
Sorry, can you see the objective again?
Sure. Well, this is for very simple case. It would be this. Yeah.
But shouldn't it be the square root? I don't know, because variance and mean have...
Turns out that's exactly the same. Yeah, no, this is, yes, you're right to be uncomfortable about this, right? That this is in percent and this is like in percent squared or whatever. Yes, you're right to be. And yes, you can replace this with a square root, which is also convex, of course. It's the norm of sigma 1/2 x. And yes, that would be much more sensible. This came about historically. It came about historically because people, if you do Western-style optimization, you can't handle a norm, a 2-norm. You can't handle a 2-norm squared because that's a quadratic, all your gradients exist, blah, blah, blah. But that's a very good point. By the way, you would get the exact same optimal trade-off curve. Different values of gamma, exact same curve. That's very easy to show, right? If I monotonically transform any of my one objectives, then of course I'm going to get the same trade-off curve. Okay? Did you get that part?
But the W might differ.
Absolutely not. The W will be exactly the same. Exactly the same. I will get the same curve. What will happen is there'll be a reparameterization of the curve by a new parameter, okay? And it will literally be a reparameterization of a curve, okay? So good question. Any others? Good. By the way, in 15 minutes, you're actually going to know a fair amount of finance and portfolio stuff. Okay, so, okay. All right, so back to this. So this would be market neutral. That would be a very common thing to do, right? Yeah, okay.
But why do we need the covariance equal to 0?
Oh, you don't need it. You should.
You put market neutral. Why? What is the physical sense behind that?
Oh, why would you do that? Oh, why would you do that?
Yes.
Yeah, because that way if I invest $10 million with you, and then I look and I see how it's doing, then one thing is the market could just go up. And I could say, wow, you're doing good. I'm going to give you a big bonus or something like that, or I'm going to pay you a big fee, right?
It's only because of the market.
Yeah,
So
exactly.
That means that we want to have such investment that it's independent of the market in the sense.
No, you don't have
In
to.
a sense.
You don't have to. I'm just saying, this is an option, and it is a common one, right, to do this. Yeah,
I'm just asking about
yeah.
it.
So, okay, so that's why. So it's not a requirement. It is one that is often chosen. People choose to do this, right? Okay, so here's an example. The same thing. So here we have leverage limits 1, 2, and 4. 1 is a long-only portfolio. That means you can't have any negative entries. And then this is the optimal risk-return trade-off. Oh, I should say that everything we're going to do today, these are all on IPython notebooks as well. So you can look at all of the code. It's all there. It's all executable. You can change anything and so on. And we'll be coming in behind with CVX scripts and convex.jl. This is to show you that actually to produce these, just to give you a rough idea, you can look at the code yourself. It's all there. But what you'll find is actually creating the plots, which are not particularly complicated or anything, is probably 4 times as much code as actually solving the problems. The problems look like the math. That's what they look like. There are 3 lines of Python. Okay? So here's an example. Here are 3 risk-return trade-offs. And of course, as you loosen your leverage limit, right, you are going to be able to do better. In this case, either go up or to the left, right? And so here are three specific portfolios with different leverage limits, all with the same level of risk, right? So there they are, and we'll look at those and see what they look like. So here they are, and these are the assets. So there's 10 assets, and you see very interesting things here. I think the blue is long only. That's leverage 1, and what you can see is, you shouldn't be surprised if you know about L1 type things or non-negative type things. It's sparse. So basically, the blue says that in the long-only portfolio, you invest 0 in asset 1 to 5. Okay? This is very common. This should not surprise you, right? And a little bit in asset 6, 7, a little bit in 8, 9, and 10, right? And these blue things add up to 1, right? Then you go to the green, which I think is the leverage limit 2, and it says, basically, it says you're going to short asset 4 because, well, for some reason, it's not good. Or rather, by shorting it, by the way, all of these have positive returns, every single one, right? So this is actually, you're betting against something that on average goes up, right? You do it because you free up the cash to put in something which is better, which would be actually, it's somehow these, right? I should point something out. This was sort of super high technology in the 50s, 60s, 70s, and it is actually how most things work now, right? I mean, so this beats a person with an MBA who sits there and says, oh, let me see. Besides, I'm doing this with 10 assets, and this is typically done with 10,000 across multiple markets, okay? So I'm just...
About covariance matrix estimation for 10,000 assets.
That's very easy, and we're going to talk about it. It's very straightforward. We're going to talk about that. Go ahead. Yeah.
So when you say the returns are random variable,
Yeah.
you look at it at the period of time, but it's not a stationary random variable.
That's also true. Yes.
So
Yeah.
if it was this easy, I mean, everyone would have made money in stocks, right?
Oh, I didn't say that, because we're going to get into the subtleties, and the subtleties are things like how do you estimate these things, right? And then they're not stationary. Well, for one thing, they're not random. But assuming you're going to pretend it's random, then it's not stationary, and you have to estimate the parameters. Okay, so yeah, there's going to be room for stuff. Yeah. Oh, by the way, I should say where mu comes from, right? If mu, that's the expected return. So there's a silly theory in economics, which is generally fairly silly, that says that mu is like a multiple of the risk, right? And they say that's the price of risk. Okay, that's a standard theory, but in fact that's actually not how it works. Mu could depend on all sorts of insider information, gigantic machine learning algorithms running that allows you to figure out for some reason that, so mu is typically your private estimate of what's going to happen. And if you run some gigantic, deep learning thing and it says that Coke is going to go up in the next 2 days, that means that mu, whatever, 237 is positive. But that's just you. Okay, so we'll get to how those things work. Okay, here's an interesting thing here. If you look at asset 8, you go long I mean, you actually buy a little bit of it in long only, but then you short it later. So the sign reverses, right? So The point is, these are actually not obvious, right? And they'll beat anything. I mean, no one could do this by hand. This is not even close, right? This is a 10 by 10 thing, so let's forget about 4,000 by 4,000. So, okay. So this variations, I already mentioned this. Actually, I think you already hinted that this was you can do things, I mean, probably you should work with this. That's the more modern thing. It's also the correct unit. It's kind of weird. Also, they plot this, so you might, the reason is the second order cone programming was not mainstream until 10 years ago, and it's still not quite mainstream, right? So, okay. You can add things like this. When you have a short position, so you own some negative shares, you're actually borrowing it. You're borrowing the shares from somebody, and they're going to charge you, right? Or if they don't charge you, they're going to have some collateral, and that's something that you have to, you can't invest or something like that. And so what that means is there's actually a cost. You can add a cost. In fact, these are not single period. You're doing these multiple periods, right? You might, in the previous period, you might have a portfolio allocation W previous, right? And so you would want, you'd actually take into account if you buy and sell stuff, it's going to cost you money. I'm not going to go into that. There's a bunch of different ways that can happen. And that would be something like this. You'd look at the difference, you'd raise this to a power, and then you'd have some positive coefficients. And very common ones are, that's a quadratic transaction cost model. They call this linear, even though it's really like a scaled L1. And then this is a very common one, believe it or not, just 3 halves. And it kind of makes sense. I should add all convex. Okay? So these are transaction costs. There's a lot of things you can do. Okay. Now, you asked, how do you estimate a 10,000 by 10,000 matrix? And the answer is they don't. So the way it's done is with they use a factor model. And so a factor model looks like this. The covariance matrix is going to be a skinny matrix F. Not that skinny. It might be, let's say, 10,000 high. Well, it's skinny, okay? And maybe 50 across or 80 across, right? So you'd have 80 factors. Then you'd have sigma tilde. That's often diagonal, but anyway, that's the factor covariance. And then you have a diagonal matrix, and it's a beautiful model, and they have great names for it. For example, this diagonal matrix, DII, is the additional volatility of asset I over and above the volatility explained by the factors, right? And so this is actually they've got a great name, which is idiosyncratic risk. Because it's the risk of that asset, it's the risk of that asset that is over and above the risk implied by the factor model, right? So, and here if you form F transpose, that's something that's small. K is 10 to 50, maybe 80 in a really big one, right? These 80 factors. And these are called the factor exposures. And a lot of times, by the way, sometimes this model is constructed by hand, by analysts. I'm not kidding you. This is done, right? In which case the matrices F are sparse. And they're done actually by some analyst. You hire somebody from economics or whatever to sit there and do this, right? And then they're sparse, and then it would be like, they would even have names. Like factor 1 would be like energy, right? And then if the correct entry in F was like 1.2, you would say, oh, that asset has a 1.2 exposure to the energy sector, okay? Right? If it was negative, I mean, that would mean something else. If it's 0, it would mean uncorrelated, right? The next one might be, defense or so, I don't know, this kind of thing, right? So that's the idea. Oh, and by the way, a lot of people actually buy these covariance matrices from a company in Berkeley. I'm not kidding. So they're very expensive. If you ever, no one's ever asked you how much does a covariance matrix cost? It's a weird idea, but anyway, they're very expensive. How do you what? Put the cost of the covariance matrix in the model. So they're not that expensive, right? It cost you $100,000 or something for a year, and we're talking about things that are where that's nothing. So, yeah. Sorry. By the way, I'm not endorsing this, right? This is also, I guess I'm mostly talking about the part of finance that is not evil. Just to place us on the ethical scale. There are entire parts that are completely evil, like fast trading and things like that. But anyway, this is not that. This is the part that's not obviously evil. Okay, so, all right. And you would say, for example, if F transpose W of an entry was 0, you'd say actually, for example, if you're a giant mining conglomerate or something like that, and you have a bunch of cash that you need to invest, you could say, actually, if you don't mind, I'd like it to be neutral with respect to, you know, whatever the extraction industry or something, right? Because it's not going to help you if, as your own profits go up and down, your investments go up and down. You might even ask for it to be might even ask for it to be negative, right? So, okay. Yes?
So if I understand correctly, this models the evolution of the covariance.
No, absolutely not. This is simply this is the covariance matrix. This is the model of it.
The covariance, then the returns are IID, this thing as well.
That's right. That's right. The returns are IID. And then if you pay, you know, to get your covariance model, and every week or every day or whatever, you get a new covariance model, right? If you paid. So, okay. Or you'd estimate it. I mean, big places estimate them themselves, right? So, and there's just no problem with this. I mean, you know, I've heard people in finance say things like, you know, oh, imagine if sigma were, imagine if you had 1,000 assets. Do you realize the covariance matrix would have 500,000 numbers in it? And you're like, so? I mean, anyway, it's kind of sad, right? And they'd say, you could never estimate that. And it's like, oh, actually, you could, right? So, I mean, of course you can estimate these things. You just use proper cross-validation. I mean, so this is, I hope I don't have to say that here. Right, so, okay. All right. Okay, so it turns out with a factor covariance model, not only is it the model people normally use, but in fact you get a huge computational advantage. I know we haven't talked about this, but in fact, I mean, because, you know, at the 0th level, the story is this. That problem is convex, done. That's the 0th order statement. And then at the next level, we start talking about how fast you can actually do it. And for example, here, if n is, say, 4,000 or something, and k is 50, right, then this is a whole lot smaller than that. I mean, not that it matters. You can do these things very, very fast anyway. But just to give you a rough idea, it'd be 3,000 assets, 50 factors. This is on there's a lot of overhead in this. You could do this a lot faster. But basically, on a single thread, little tiny solver, this might be 10 minutes to solve that problem. And if you have a factor model, it's down at half a second, right? Just to point this out. And this is a secondary thing. The level 0 idea is convex. We can solve it, okay? So, okay. Next topic is worst case risk analysis, and it's related to this, and it's a pretty quick. So we're going to do Markowitz portfolio allocation, but this time we're going to have a fixed W, and we're going to come back to some questions that were asked about how do you model this covariance matrix, right? And the point is that you don't know the covariance matrix really. And there'd be lots of ways to analyze it and things like that, right? I mean, if you really believed in probability and statistics, you know, if you really believed it, you'd say, well, actually, sigma would have a Wishart distribution, right? Because that's what it would be, right? Because it's from estimating from things. That would be the error distribution of W would be Wishart. Okay, or sorry, yeah, the posterior would be Wishart. Okay, so we'll do this another way. What we'll do is we'll simply say we'll have a set that describes the set of possible covariance matrices, right? So you would say, well, actually, I do believe I know the actual diagonals of these things within plus minus 5%. That's reasonable. But you see these two here. When you look at an asset and you say these things are 20% correlated, you say, then you poke the person, you know, an analyst, and you say, do you really believe that? And they go, no. It could be anywhere. I said, could you believe 5%? They go, yeah. If something weird happens, yeah, it could be 5%. Could it be 80? And they're like, yeah, it could happen. That wouldn't be good, but it could happen. So basically, you get a set. You have a description of what the covariance matrix could look like, right? Okay. And then what you do, the risk is this thing. Now, that's a quadratic function in W. But if you look at this as a function of sigma, it's linear. That's a linear function in sigma, right? If you fix W, that's a linear function in sigma, of course, right? So that says, now we're going to do stuff like this. We're just going to maximize this over over the covariance matrices we believe can happen, right? So this is pessimization, right? This is getting the worst possible answer, right? Okay, so what you do is you simply maximize this, and the variable here is sigma, right? So this is actually a convex problem, right? Because you have, you're maximizing a linear function subject to sigma being positive semi-definite, and sigma in the set of covariance matrices you believe. So that's it, right? And then you solve this problem, and if the worst case risk is not, if this is not too bad, then you can worry less, right? If it's terrible, then you can go back and look at your assumptions in S and either tighten them or do something else, right? So that's your option, right? Or increase your risk aversion in your portfolio construction. Yes?
Wouldn't it be more sensible to also have some kind of probability distribution on sigma?
You know what? I don't think you could do that. Absolutely. So that you could do. I actually don't think so, because the nice part about the worst case one here is you're doing an end run around this essentially religious and false belief that this is a random variable, right? So this actually is probably, if I were going to do this, I would do this.
It's a little bit more pessimistic, but you also believe that sigma is actually an S. So you're making
You are no, that's you're right, right. So, but yeah, you could do that. People do that. People have a distribution on sigma. It's getting kind of weird if you think about it at that point, right? So,
but I could, for example, also cover like I could make S bigger.
yeah, yeah. So I think actually it's a good question, and I'm going to answer it this way. This goes back to the idea of uncertainty and robustness, right? And I think, so a general story across all of applied mathematics is really simple. The first person on the scene gets 80% of the credit. The simplest, dumbest method you can imagine, right? You throw in regularization. You get 80% of all the... Then more sophisticated people come back, and then people start arguing about whether they should have a probabilistic model of the uncertainty or a worst case model, and then the religious wars happen. And it doesn't matter, because the first person who showed up on the scene and said, hey, dude, you don't know sigma, right? That was actually the critical achievement. So, but yes, so I would call those second order questions. But yes, you can do that, and people do. So, okay. All right, so let's just do a quick example, and it's just to show that this is not remotely obvious, these things, right? It's a baby thing with 5 assets. Here's your allocation vector. You're short in the second one. This has a leverage limit too, and this is actually optimized for some, here's the nominal covariance matrix, right? What we're going to do, just to make it simple and it fits on a slide, is we're going to say the following. We're going to say that every one of the off-diagonal numbers could be off by plus minus 0.2. Okay? That's our model. Okay? Just to make it simple. You could make it much more complicated if you wanted to. And it turns out, by the way, if you do that, you would sort of, and then you ask, what's the worst case risk with this fixed portfolio? You would guess that the answer would often be with the sigma i's, all of them should be at their extreme, right? If I tell you that the correlation between 2 assets, like Google and something else, right, is an apple, if I tell you it's 0.6, and then tell you, well, now let's find out what's the worst possible thing that can happen, and I'll let you range that from 0.4 to 0.8, you would say, well, why would it not be 0.4 or 0.8, right? So, all right. And it turns out, for this example, here's what happens. Your worst case risk is twice what it is under the nominal model, and here's the worst possible perturbation. Now, all of these make sense. This is weird, right? So that says that this will actually give you the absolute worst, the worst thing that could happen in this one. That could have ranged between minus 0.2 and plus 0.2. But the absolute worst thing to happen is that it could be minus 0.08. Okay? So actually, my only point here is just very simple. This is not obvious, right? No human being could figure this out. Right?
Is this because we are optimizing static?
No, we're optimizing a linear function. We're not. So it's even weirder, because when you optimize linear functions, you should be on the boundary. We are actually on the boundary. We're on the boundary of the positive semi-definite cone. So that's it. Okay. All right. So that was an example. Now, at this point, we can do a couple things. We could power forward. There's
By the way, this
yeah.
is equal to 0.02. It seems there's some correlation there. It would be like greater than 1 when you add it.
Yeah, but we add, no, actually they wouldn't be. These were not correlations.
It's covariance. Okay.
Yeah, sure. These are covariants, and we have an additional constraint that the worst case covariance is positive semi-definite, right? So of course, yeah. But yes, if it were correlations, yeah. But actually that would come out because it'd have to be positive definite, right? Or a correlation matrix anyway. So, okay. So,
And where did you,
Whoop.
how do you check the constraint that
convex. So we don't, how do you check it? That's easy.
No,
You do a Cholesky factorization.
Which condition you put to take it into account?
You mean this?
Okay.
Yeah. So, yeah, so actually a lot of this, so let me point out, that's a good question. It triggers me to say something. So actually the style of this style of applied mathematics is, it's declarative, right? So notice that I'm not telling you some silly algorithm about, oh, here's my algorithm, ready? Take the perturbations, then find out what the risk is, take the gradient, step in that direction, and then project, and then I could bore you with a proof of, that this would converge. And so you don't do that. You don't do that. You simply say, please maximize this function over these constraints. It is convex, and therefore, many, many solvers. Where's my person who's going to ask how you do? Okay, anyway, sorry. I'll assign you this time. Okay, then there are many solvers that will solve it, and they will all get the answer, period. Okay? And then, so that's how, so it's just declarative. We just say what we want, and again, if someone were, if I give this at a finance thing, people will say to me, how do you do that? Did you use projected gradient? Again, the answer is usually a polite version of none of your goddamn business, right? That's a macro for. That's a great question. There are actually many, many algorithms for solving convex problems, and they all work, right? So that's the polite form. So, okay. All right. Okay, so we could do this, or maybe we could let me come back to this, because I'd rather do one that's, yeah, we'll go to some model fitting, and then I'll come back. So what we're going to do is we're going to look at, we're going to look at some variations on regression, right? This will be close to machine learning. I mean, this is model fitting. So, and maybe it'll be something you haven't seen, but it also just shows you how easy how simple these things are once you get this. So we're going to do standard regression. So you're given a feature vector and a label. That's going to be real, and those are going to be real. And we're just going to fit an affine model that looks like this, right? So it's just an affine function of the features, right? And the residuals are going to be your model minus what you observed. And for example, if you do least squares or standard regression, you would minimize the sum of the squares of the residuals. And that's a convex problem. It's least squares. It's the oldest convex problem there is. And you know that you'd get something that's sort of unbiased, right? You get something where the optimal residuals is 0, right? So for example, there's no regularization here, right? But in this case, you'd get something where, at least on the training set, the average value of the residuals is 0. I'm mentioning that because we're going to come back to that. Yeah.
Sorry, it was about the previous slide.
Okay.
Can't you jointly optimize the...
Yes. Yes. So that was a great question. I'm glad you're asking it. So I showed you how to optimize portfolio, assuming you know sigma. Then we switched it around, and we said, let's fix W and find the worst sigma. And the natural question then is, can you do the following? Can you do minimax design? Can you choose W of that? And the answer is yes, you can. And it's a convex problem. I'm not going to go into details, but that's a great question. Yeah. And yes, you can. It's more complicated, though.
So it's kind of robust optimization.
It is indeed robust optimization. Exactly. Right. Okay. That's a good question. Okay, so, all right. So you can add ticking off regularization or ridge regression, depending on which subfield of these things you come from, and you would minimize this, and you'd also say, please don't make my coefficients too big. Okay, so that would be that. Right? And you'd choose lambda, presumably by cross validation. Right? That would be the correct way to do it, and the incorrect way to do it would be to throw some theory at it. Right? That would be the incorrect way. Although, as long as you do both, it's okay, in my opinion. And if I'm trying to mess with you, that's exactly what I'm doing. So, okay, fine. Okay, so here's a simple variation on this. I don't know how many people know about this, but you replace least squares, right? There's a square function with a Huber function, and a Huber function is this. It's something that is least squares up to some threshold, like right here, and then above that it continues linearly. So actually, how many people have seen this? Okay, good, lots. Okay, so basically, I'll say the following. If you're ever doing data fitting and doing regression, you should not be. This is what you should be doing, period. There's essentially no exception to what I just said. Okay? So let me explain what it is. It's a function, it's convex, right? It's a function that looks like least squares for small residuals, but if you have a big residual, the cost is linear. And if you think carefully about what that means, it means this. Ordinary, I'm going to anthropomorphize model fitting. And basically the square function is telling you how irritated you are for a given residual value. If you take square and you have a large residual, then you are large squared, which is you are very irritated. Everybody got that? Okay, so on the other hand, if you look at a Huber thing, if you have a large residual, you are irritated, but you're not very irritated. I don't know if that, right? Very is, large squared. Okay. So there's a lot of theory behind this, and this solves some mini-max problem over probability distributions and blah, blah, blah. But the point is that actually what it does can be completely understood on a completely intuitive basis. This is actually very simple. Okay, so if you do Huber fitting,
Wait.
yes?
Where do you get M from?
Where do you get M from? Same, you'd cross-validate. That's the answer, yeah. There's actually several ways to get M, but really the only correct way, cross-validation. So I think, isn't that the answer to everything? How do you get hyperparameters, right? And the answer is you cross-validate, I think. I don't know of any other answer. In some cases, you can also pretend and throw papers at someone until they, you say, here, read these 25 papers, but the bottom line is you cross-validate, I think. I mean, you tell me if I'm wrong. So, okay, all right. So we'll do an example. It's a very baby example. Again, you can just look at the source code. It's very short. So we have something with 300 regressors and 450 measurements. So it's not like we have a lot of measurements compared to the number of regressors. And what we're going to do is we'll choose a true beta. And the x's will just be, the feature vectors are just going to be normal. I mean, this is optimized to fit on a slide, and also so the code is like 7 lines instead of like 12, okay? So that's the choice of this. And then we'll set the measurements to be, we'll generate them from the true model, and then we'll add another noise here, right? Now we're going to do something simple. We're going to add outliers. But let's talk about outliers for a minute, right? If you look at a data set and you look at a bunch of y's, and they're all in the range of like plus minus 1, and all of a sudden one is 1e plus 8, you know it's an outlier, okay? So anybody could write a simple script, and anybody who actually does any real data would do exactly that. You'd have something there that would say, hey, I bet a high order bit flipped because this one measurement is 10 to the 8 times bigger than all the others. Everybody see what I'm saying here? So anyway, anybody, a high school student, could remove outliers that are off by a factor of 100 or more. Okay, right? That's obvious, right? If an outlier is really small, it'll have no effect because it doesn't really make any difference. It could have been the noise, right? So in fact, the issue with outliers is this. The worst thing that can possibly happen with an outlier is this. It's a measurement that is plausible and yet completely wrong. Okay? So that's actually the only danger with outliers. Okay. Okay, so to do that, to make things that are plausible but completely wrong, we're simply going to do this. With probability p, we're going to replace y with minus y. And because these things, the features were generated with 0 mean, that means that the distribution of all the y's is identical. And that means these are not obvious outliers at all. There's no way you could look at them and say, oh, look at that. Measurement number 17 is wrong. There's no way. Okay? So everybody got this? This is actually important. Because it means we're making a problem that's actually quite challenging, okay? And wouldn't work with the naive test. Okay, so what that means is we have a fraction p of non-obvious, completely wrong measurements. They have same good and bad distributions. And we're going to try to recover this beta true. And then, by the way, we're going to compare this against the prescient version. The prescient version is that I give you 450 measurements, but I'm going to tell you which of them were wrong. That's going to be an unbelievable advantage, right? Because it means you could switch them back and then solve the full least squares problem. Everybody got that? Right? Which would be maximum likelihood in this case. Okay. So this is just a weird random example. First one we typed in. We didn't run this for a while until we got something that was spectacular, but this is very typical. Here's what happens. This says the red is the prescient value here. Actually, you can see it on another scale. We'll get to that in a minute. But here, let's do this. This says if you simply use least squares, then obviously, as you get 2%, 4%, 6% of your measurements are completely wrong, but plausible. Of course, least squares is going to start failing. And what you do is you start getting, you get much, much farther away. This is the relative error in your estimation of the parameter, okay? So this, I mean, this makes perfect sense here, right? Here's what's this, the red, we'll zoom in on this, but the main thing is the green is this, and what it says is you can tolerate up to like 6% of your measurements are completely wrong. And just by changing the objective to Huber, it's just nailing it. Everybody see this? If you're not impressed with this, then you don't understand what's being shown. Okay, so those are the only two possibilities, right? So here's what it looks like here. And I mean, so, and this is typical. I mean, they all look like this. I mean, this is kind of what happens. And you know, you typically at some point, of course, you can't have that many. But you see, I mean, if you look at this, this is extremely impressive. This means that when 7% of your measurements are completely wrong but not obvious, you're actually doing, you know, not that much worse than if somebody came along and actually told you exactly which measurements were wrong, which would allow you to correct for them. Everybody see this? So this story is repeated everywhere, right? And the worst thing that can happen is it reverts to least squares. Yeah.
Like, knowing that it's kind of pretty obvious, not from looking at the data, but from the algorithm side. So
yeah.
if you use ransack,
Absolutely.
you do it always.
Yes. Yeah. That's a good question. Yeah.
Probably up to 10% or 20%.
No, you're right. You're right. Yeah, sure. No, I'm not saying that there's other ways to do this, and indeed ransack would work quite well. Sure. Yeah. Actually, what's nice is you don't do it for just this. We're going to do it for lots of. It means once you have absorbed this, you can now do it for hundreds of problems, for classification problems, for all sorts of other stuff. Right. So that's kind of the idea. Yeah. Oh, and by the way, you can improve this considerably. Because all you do is when you've actually made an estimate here, you go back and you figure out which residuals are in the linear portion, you flag those as thing, and then actually this thing will actually be the same as ransack. It'll actually be better in a lot of cases. So, yeah.
So linear is the best we can do, right? If we go below, it becomes not
That's a great question. That's exactly it. So it's not the best we can do. The function we would really like to have here is this, quadratic and then constant, right? Yes. Right, exactly. Good. You've absorbed the, yes. Yeah. So an office neighbor of mine had a student in his office, and they were doing information theory, and the professor said, but you could do this, and the student stepped back, and he said, you can't do that. That's not convex. And anyway, then the professor came to yell at me. He said, well, look what you're doing to these students. They're terrified. You're ruining them. So, okay, fine. Okay, we're going to look at one more, which is quantile regression, right? So this is also fun. Again, probably some people have seen this. Yes.
Can I ask a question to you?
Yeah, sure.
Do you have the same perturbation in the test set?
What's that?
Do you have the same kind of perturbation in the test set?
Yes, absolutely. Yeah, same. Yeah. Yeah. Okay, let's go to this one. Yeah, so same, even same size. So, yeah. So we'll look at quantile regression. So actually, how many people have seen this? Because it's like super elementary convex optimization. And if you do model fitting, and don't say you don't if you're in this room, you do model fitting, right? Then you should know about this. It's just super, it's really simple, it's intuitive, beautiful. So I'll show it to you. So here it is. What you do is there's a tilted L1 penalty. So L1 penalty is this, it's absolute value like that. And then all you do is you tilt it. So what it means is you put more or less weight on over or underestimating. That's in an estimation context, but just being positive or negative, right? So there's L1, absolute value. You know, here it is for 0.1. And this says that you're gonna consider it much worse to underestimate than to overestimate, okay? And then this one would be 4.9. And here's the function, all convex. And this one, you're going to consider it much worse, actually 10 times worse or something, 9 times worse, 9 times worse to overestimate than underestimate. Okay? So this is the idea. Very, very simple, very intuitive too. And it's clear what's going to happen if you do this, right? What's going to happen over here is that when you're asked to fit something, the residual distribution is going to be pushed over to the left. And over here, the residual distribution is going to be pushed to the right. Okay? And this will be somehow balanced. We'll see exactly how, because it's very simple. So it turns out, when the residuals are not 0, the partial derivative, let's just take the offset. And if you take the partial derivative with respect to the offset, it's very simple, right? You take the absolute value of a number, and then you subtract, you simply subtract this offset. And what happens is, it's got a slope tau for the positive ones, and 1 minus tau for the negative ones. So it's exactly this, right? It's a piecewise linear function, and it looks like that. Now, when v is optimal, roughly this is 0. That's not quite true because this takes on discrete values. But roughly speaking, if there's an odd number, I think it is exactly true. But then it goes like this. Then it says, if this is 0, it says that tau times the number of positive residuals is 1 minus tau times the number of negative residuals. And if you take that, if you add, you add tau times the number of positive residuals to both sides and everything, and you end up with this. It basically says that a fraction tau times the total number of residuals is equal to the number of negative ones. And what that says is that the tau quantile of the optimal residuals is 0, right? So if tau is 0.5, it says that the median is 0, right? So if we go back to this, if I do L1 fitting, then the median, by the way, this is the L1 analog of simply saying that the average of the residuals is 0 for least squares, right? So there, you're unbiased or whatever, at least on the sample set, right? You're unbiased. Here you're saying that the median is 0, the median of residuals. And when you choose tau not equal to 0.5, it says it's even more beautiful. It says that the tau quantile of the residuals is going to be 0, right? And so this justifies the name that this is quantile regression. Okay? Everybody got this? It's very beautiful. Okay. So just a quick example to see that this does something. We just made a time series up, and whatever it is, it's like 3 lines of Python, not fiddled with too much or something like that. But we just made something. And then we're going to make an autoregressive predictor. So what we're going to do is we're going to approximate the next time series element by a linear combination of the previous m, and then with an offset, right? And we'll take m equals 10, right? So we're going to do a linear prediction to predict the next time step based on the last 10. And we'll use quantile regression for tau equals 0.1, 0.5, 0.9, and we're going to get 3 different predictions. Okay? We're going to get this one, the centered one, the 0.11, and the 0.91. And these are essentially predictions of quantiles, right? And so here's our time series. I mean, we just made it up. It's something, right? It doesn't matter. But whatever it was, it takes 3 lines or 2 even, something like that to generate. It's interesting, and not exactly given by a linear regression, right? So there it is. There's your time series. And now you simply fit the 3 models, and you get this. So what it says is you're going to get the blue one is your high predictor. That's your 90% quantile prediction. Your red one is going to be your 10% quantile prediction. And then the green one is going to be the median prediction, right? And so what that means is if you think about how would you use a one-step ahead predictor, you're in some situation and you'd like to know, what's going to be the demand for electricity tomorrow. That's what you want to know because you have to schedule generators tonight, right? And so what it says is you're going to get 3 predictions. You're going to get the median, a 90%, and a 10% one, right? Very cool, right? So let me zoom in on this and we'll see this closer. And this is how it works. And it's quite beautiful. This is on the test set, right? So here it is. And you can see actually very interesting things happen. For example, the difference between the 90%, the high prediction, the low prediction, and the median actually is much larger sometimes than other times. Nothing happened. This is just like the dumbest thing. You type in 3 lines of Python, and you solve a convex optimization problem. So this might be a good time for somebody to ask, how did you? No, I'm kidding. Okay, right. So everybody got this? So it's actually kind of cool, and it's weird. I've actually shown this to various people who use these kind of time series stuff all the time, and they were like, they would turn to their colleagues and say, "Why don't we do this?" And they would all look at each other and they go, "I don't know." They're like, "We should do this," and they were like, "Okay." So anyway, so So this is something simple. I mean, there's a lot of fancy theory about this too, but it's completely intuitive how it works, very simple, and it's kind of cool. It means you get a range. I'm going to give you not one, but a range of predictions. So, any questions about this? No. Well, let me show you let me show you this thing, and then I'll come back and say something. Okay. So this would be the training set. And of course, it's exactly what we say, right? That this is for this is our low prediction, and sure enough, look at that. It's exactly 0 at the 10th percentile. These are the histograms. Our medium set has exactly half the residuals positive, half negative. So you're under and over exactly 50% of the time. And sure enough, our high prediction is wrong, is above the actual value, basically exactly 90% of the time, right? This is on the training set. And you get something similar on the test set, right? So, and it's the same thing, right? So this is the idea. Yeah. Okay. So this makes sense. So, well, okay. I've never shown this before, but I was hoping like a Bayesian was going to step up and say something. No. There are some here. I know it for a fact. Good.
Shouldn't I get the content for free on Bayesian?
Yes, thank you. And the answer is yes. Right. So for Bayesian, they're like, so what? Compute the posterior distribution, look at the 90th quantile, done. Okay. No, I know. And the answer, and my response is, yeah, that's absolutely correct. Yeah, that's right. So, okay, good. But why didn't you say that? I had to prompt you.
Try.
Okay. All right. You don't have to be. Okay. So now we actually could do one of two things. We could either look at some general model fitting stuff for fun, which would be kind of in the same way. It might be fun. Or we can go back and do optimal advertising. My suspicion is we don't have time to do both in a good way. So it's your choice. Model fitting? I didn't hear anything else, so. Model fitting, good. Okay, we'll do model fitting, right? So, and again, this is going to be very close to stuff you all know about, right? So, but it's just it'll show you a different way of doing this, right? So, okay, maybe not. So you have a bunch of data, which are pairs of a feature vector and some outcome or label. Could be real, could be Boolean, could be categorical. I mean, it could have a finite set of. It doesn't matter. It could be like a parse tree, for example, or something like that. It could be a complicated object. It doesn't matter. And we're going to find a model or a predictor. That's a function that maps the features into the outcome or label set. And we want to do this for data you haven't seen, right? So, and if this is R, that's just ordinary regression. If that's, some Boolean, then this would be a classifier and so on. Okay? And then you're going to choose this thing based on observed data and prior knowledge. I mean, this is kind of, okay. And loss minimization goes like this. I'm not going to say anything about the theory behind it and all that kind of stuff, but this is what it looks like. So the data is going to be parameterized. I said the model is going to be parameterized by some vector theta. Then we'll have a loss function. And then we'll just simply, the loss function is going to define everything. So this is going to be the loss or misfit for the data point xi, yi if you use model parameter theta. And then what we can do is you choose theta. Once you choose theta, that locks down the model. And the model is going to be really simple. It's going to be you minimize over your labels the loss for the given x and for the given theta. Okay? So this is, again, this should be, I guess this is kind of standard. Okay. And then a very general way to do this is you do this via regularized loss minimization, right? So we're going to add a regularization. And we'll let it be infinity, and that's allowed. That's there so that we can put constraints on the parameters, right? For example, some chunk of the parameters might be a covariance matrix, and then we need that to be positive semi-definite, right? Or it could be some sources, and they have to be non-negative or something like that. It doesn't matter. Okay. And we'll simply minimize the average loss plus the regularization, right? And then for a lot of useful cases, this is a convex problem, right? So this is the idea, right? And then we don't, I presume people have seen this sort of stuff, right? And you get things that look like this. And I think this is how it's taught at Stanford, and I presume this is how you learned a lot of it. Right. Yes?
Could you go one slide back?
Yes.
Are we trying to find the best data as parameters?
No. What I'm saying is this is how we are going to find theta.
Right, but why is the model then the argument over y?
In this case, theta has been locked down. It's chosen.
Okay.
And then this is the model. Right? So it could be a bad choice of theta, it could be a good choice of theta. Right? If you choose an inappropriate regularization or an inappropriate value of lambda, this theta could be terrible, and this model will be quite poor. Okay? So here, we've fixed theta. Right? Yeah, but yes, we are, so this is sequential. We're going to choose theta by minimizing this. Theta is now locked. I probably should have written theta star or something like that, you know, there. And then it would have been clearer. Right, good. Good question. Okay. Okay. And then you can plug and play and make all sorts of things here. You can do regression and all sorts of stuff here. And I can make ridge regression. You can make classifiers. You can make all sorts of fancy things this way. And you can mix and match losses and regularizers, right? So that would be the... Actually, how many people saw something like this? I mean, I hope it's a lot. Right? Okay, good. That is a lot. Good. We'll keep it that way. With convexity front and center, I'm assuming? No. Or yes? Yeah. Okay, good. Good. All right. So, and then it means now you can do all sorts... And actually, it's good because once you understand that there's that there is a playground, you know, there's a sandbox you can mess around in. And basically the sandbox that has to be convex in theta for fixed x and y. And then that has to be convex in theta. And as long as you stay in that sandbox, you're going to be able to solve this problem. And now the choice is, you know, you should figure out how to choose R and how to choose L, right? That's going to be what you're going to want to, what you choose. And you'll choose that to fit the data, to fit the problem. And you can check it by cross-validation, period. That's the right way to check it. So you'll know if you chose, you know, if you ask like, well, what's better, logistic or SVM? The only answer is cross-validation. That's how you check. Okay? So that's the picture, right? Regularizer, again, choice of particular regularizer, you know, you could take a fashionable one, like, what's it called when you mix these two? That's called? Come on, it's super fashionable. What's it called? Elastic net. Yes, of course, you can do elastic net, and you could throw in a third term, which would be the absolute values of thetas to the 3/2. And then someone would say, what's that for? And you go, I don't know, because it's weird and cool and we can do it, or something. I don't know. And then you'd have to find some case where that outperformed something else, which you wouldn't, but you could try anyway or something. So, okay. All right. So we'll just do a quick example here. And we'll do something with a bunch of Boolean features in, just 10-dimensional to make it simple. A Boolean outcome. And we'll make a feature vector which is all products of the co-occurrence of the original features, right? So, and of course on the diagonal, those are the original features, right? Because it's zi squared, which is zi, right? We'll use logistic loss, L1 regularizer. It just really doesn't matter. And then what we're going to do is we're going to have, L1 regularizer will do a nice thing. People here know about that. It will sparsify the model. And what that means is it's going to select, in this case, it's going to select pairs or interaction terms or however you want to call it or something like this. And we'll train it on 200 examples and test it on 100 or something. And you get pictures that look like this. And this is exactly what you want to see, right? That the test and train errors are, comparable. And if you're wondering what this is not the objective function. This is actually the fraction of errors you make, right? So otherwise, of course, the train error would have been monotonic increasing, right? So it's not that, right? So so you'd say, okay, well, our best parameter value is somewhere in here, and it turns out it chooses these. So there, it says you don't even need. You do need ZOO2 because you have this, right? So here you go. You certainly don't need. No, sorry. The only one you don't really need is 10, right? So we're only showing the upper triangle, right? So it says that you don't need some of the features, and it says these are the interaction terms you want, right? So So just for fun, how would, suppose you wanted to use as few interaction terms as possible, but you're okay using the diagonal terms. What do I do? I use all the z's. I can use all the zi's, but zi, zj, I want to be sparse with those. What do I do? What do I change? What do I change? What's that?
Just have a regularize on the
Yeah,
product.
but we have a regularizer. It's the L1 one. So make a suggestion.
You use it on the product.
Oh,
Only
okay, on the cross, you'd have a second regularizer on the cross term. That's exactly it, yeah. So anyway, this is kind of the idea. Okay? So, all right, so this is kind of the idea. Okay, so this I think is very close to things you've seen. And I think what I'm going to do now is actually not go back and do the last example. What I do want to do, though, is maybe this would be a good time for, since this is kind of the end of the course, this might be a good time for us to have questions, if you have any, or complaints, or anything else. Yes?
How do you solve those models?
What's that?
How do you solve those models?
Oh, yeah, how do you solve it? Okay, yeah. That was a joke, I'm assuming. Okay, good. Great. Right, so I could tell you, but yeah, so it was converted into, the original thing, CVX pi parsed it into some cone program with the exponential cone, and that was solved with a primal dual homogeneous embedding solver written by someone from ETH. There, that's the actual answer. But you could have used another method and you would have got the same thing.
This might be a really stupid question.
No.
But what happens if like two of the features are super correlated or almost the same? Like which one?
It's very interesting what happens. In L1, it will tend to choose just one, and this is why people would use elastic net if you have some problem with that, right? That's exactly right. If you have a whole bunch of features and some are correlated and use L1, it's going to probably choose one of them, right? Not randomly, by solving a convex problem, but it will appear random because you'll change the parameter, change the data, or if you're doing full cross-validation, sometimes you'll use, this feature and sometimes that, sometimes this one, sometimes that, and it'll appear random. And if you put in elastic net, then it's going to be more stable that way. So that's actually not at all a stupid, that's a good question. Yeah?
So you were telling us like yesterday how to know if a function is convex.
Yes.
But the problem is that the functions you were showing were not like, we don't have the subject to constraints.
Right.
So is there also like a clear way, like when we talked about yesterday, to know if
Everything comes down to the same question. Is a function convex? Because here are the things you can do. Or concave, or affine, which is both. So because here are the problems you can solve, right? It's very simple. You can minimize a convex function or maximize a concave function, right? And affine promotes to either, right? Subject to some inequalities, which can only look like this: convex less than concave or concave bigger than convex. Or affine equals affine. That one's actually redundant, because if you go affine equals affine, you could write it as less than or equal to and bigger than or equal to. Affine promotes to both convex and concave, and so it'll match. So syntactically, that third one is not even needed. That's it. And you do it separately. So they're not coupled in any way.
Okay, and it's doing stuff like taking the Lagrangian, so like we can take out of we can put those inside the formula, and then if the formula is concave, then
That's all, you're way too low level. We don't, that's like assembly language. We don't, if your problem is convex, you can minimize a convex function subject to constraints. If you want the optimal trade-off curve, you can vary the constraints and minimize something. You could make a weighted sum and minimize it and vary the parameter. You don't have to form Lagrangians. If you want to, you can, but it's not a big deal. There's no advantage, disadvantage to doing it or not. None. Yeah. So we consider that to be lower level, right? So, yeah.
So what happens if one of your, this sounds like a maybe stupid question, but what if you have an equality constraint on a norm?
Yeah.
On a norm to be,
Well, you tell me.
is it something about the domain being convex?
If you have an equality constraint on a norm, that's really simple. It is not convex, because the only equality constraints you can have are linear. So that's just end of story. Now, there are some cool things you can do. So it turns out if you have an inequality constraint, if you have an equality constraint on a norm, like norm equals 1, no good, period.
But
But-
for example, eigenvectors.
I'll tell you about that in just a second. So the first thing this is something that very often happens, is you can relax norm equals 1 to norm less than or equal to 1. And very often, you can even prove before you solve the problem, the solution's going to be on the boundary. In which case, you actually solve the problem with equals. Did you get that one? Yeah, and then the eigenvalue problem, there's a weird story behind that. So, and it's a great one, I'm glad you asked it, right? So it goes back to a big picture question, which is this. So there are people who are extreme, who simply say, the only continuous optimization, actually they go even further. The only computations you can actually carry out and get the answer are convex ones, period. They're just period. And then you'd say, but that's ridiculous, because look at PCA, singular values, I can solve that problem exactly, and that's not a convex problem. And then they would come back, this is a bit weird, and they would say, but the dual of an eigenvalue problem is this: maximize X transpose PX subject to X transpose X equals 1. Now, you got a lot of problems there, right? Because the objective is not, concave or convex, and the constraints are not affine, right? So then they would say, but the dual, which is a semi-definite program, has zero duality gap. So, you see, when you actually, you didn't know this, but when you're solving if you're doing PCA or doing SVD, you're solving a convex. I think that's kind of nonsense, but anyway, so there is that weird connection. Yeah.
Are there any groups within non-convex problems, and can we solve some of these groups of problems?
Yes. Right. So yeah, there are. Actually, I just mentioned one. There's a whole lot of problems where you form a convex relaxation, and then in the simplest case, you prove that no matter what, making some assumptions about the rest of the problem, they'll be tight at the solution, and then you've solved a non-convex problem by solving a convex one. So that's one case. There are other interesting methods where you can't prove it ahead of time, but you can do it on a case-by-case basis. Those are very interesting, too. So yeah, there are lots and lots of cases where you can do that. Then there's ones where you have approximation ratios and crazy stuff. So there's a lot with that. Yeah?
I think it would be possible for these kind of modular programs to get a non-convex problem and to find the best convex relaxation automatically.
Yes.
Modular kind of way of
Yes.
creating things.
That's a great question, and actually that's technically what happens, right? So when we compile a problem into a cone program, the actual cone program we're compiling to is actually a relaxation of the original problem. If the original problem was DCP compliant, so that means all the monotonicities and curvatures lined up, then we can prove that that relaxation is tight. In other cases, it's simply a relaxation. Right now, in the solve method, there's an if statement that says if it's not DCP compliant, we throw an exception.
But you could replace that with this.
If you just plowed ahead, it would just solve a relaxation. And then, if it turned out to be the feasible, congratulations, you just solved a non-convex problem. Yeah. That's a great question. Yeah.
It might be so a bit stupid, but let's assume we have some data sampled from some target function, and then we don't have access to the target function, but we want to optimize it. So that means, for example, we can construct a regression using this data, and then optimize the regression to find.
Sure.
But the problem is that regression, like kernel, it's not convex. So how to make, in a sense, a convex approximation?
Well,
Using data sample.
certainly the following problem is completely tractable and easy to do. And that's this. I give you some data, I tabulate some data, and I ask you to fit a convex function to that data. That we can do globally in practice and everything. So that I can do. That's simple enough, right? Because it's just, well, we can just do it. Let me put it that way. Now, what happens is if your data has if, for example, the worst thing is your data actually comes from a concave function. What you'll get is you'll get an affine approximation. Because the best approximation of a concave function by a convex function is going to be affine. But in general, it might be something where it goes like this. It has some regions of non-convexity, of negative curvature, and you'll just get a model that kind of splits the difference. But that's a great question, and that we can do. That's not a problem. Yeah? You looked like you had a problem forming. You did, I think. No, this is good. This is the time for general questions.
Sorry?
This is the time for general questions. That's great.
Okay, okay. So what if, could we take the outputs of the optimization problem
Mm-hmm.
and then input into some machine learning problem and then solve it more? Is it possible
To take the.
to take the partial results of the optimization algorithm
Mm-hmm.
and then to insert it in some machine learning algorithm and solve it?
No, there are things like that you could do. Repeat the question. So the question was, could you take something like an output from an optimization problem and then feed that into a machine learning problem, right? I think the answer is yes. I can give you an example of where that's done, if you like. So in control, you saw an example of control. In control, you might decide, you might have to solve a problem. You're going to look 50 steps in the future and you solve a problem with a couple thousand variables. We could do it fast, but maybe not fast enough because we have to make this, we're running a jet engine and we have to make this decision every 5 milliseconds. Everybody got this? So, but we can do it in a half a second, right? So here's what we do. We set something up where we take a whole bunch of initial states. We solve the problem each time for initial state, maybe on a whole bunch of different, different processes running. We have a whole bunch of threads fired up. And we go to lunch or we go to dinner or we go home. And you come in the next morning, and now you have, what you have tabulated is a set of solutions for different initial states, right? Say 100,000 of them. Got it? And now what we do is we take that and we fit that, just like this, with a simple function. And now we have a function that can be evaluated in, let's say, 100 nanoseconds, not 1 second. Is it the exact solution? No. But so people do that quite often. And so I think that does match what you said.
Yeah.
Okay. Yeah, and it's an interesting thing to do. So I think, have we come to a stationary point? No. Okay, good. Yeah, that's fine. Yes.
My question, it could be like if you consider the sum of some convex functions with positive coefficients, for example, and this is convex function
Mhm.
kind of basis.
Yes.
And vocabulary.
Yes. A dictionary.
Dictionary, yeah.
Exactly.
Better.
Right. Yes, so that is one way to do it. You can actually do you can actually solve the non-parametric problem exactly.
How? I mean,
Look in the book. So,
come on.
yeah. No, it's not the kind of thing I'm going to do here. Yeah, but you can actually solve the infinite dimensional problem, which is this. I give you some data I give you some xi and yi, and you say, please minimize over the infinite dimensional class of all convex functions, something that minimizes the least squares deviation, f of xi minus yi, quantity squared. So, and that's the non-parametric infinite dimensional problem, and that can be solved exactly. But this is not the time or place for me to go into those details. So, yeah.
This is more low level, so
Okay.
For example, if you have a least square problem with a two-cone regularization, it has a closed form solution, right?
Yeah.
But people still sometimes, even for small problems, use gradient descent or something else.
Right.
Don't you think that's an overkill? Like why?
Right.
Like,
I'm.
isn't it the danger of using just a prepackaged thing to solve everything?
So I'm glad you brought that up for a couple of reasons, right? Because if you look at, for example, the Huber thing, and you said, why wouldn't people use that? People sort of classically trained would say, oh, but least squares, we know there's an analytical formula, and that allows us to understand everything about it. Asymptotic statistic, blah, 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 all this stuff, right? And they'd say, and because we have a closed form expression, it's faster to compute. That last statement is false. That's false. So the complexity of doing Huber fitting or any of these things is the same as least squares. So that's the case. If it's okay, it's perfectly okay to use, stochastic gradient to solve a least squares problem. It's okay. It goes back to the question that was repeatedly asked after I prodded people. How do you solve that? And stochastic gradient is a perfectly good way. Totally good. I mean, it has certain attributes. You'll never get high accuracy. But in machine learning and statistics, you don't need high accuracy. Right? Everybody knows that, right? And you don't have to be embarrassed, right? This is true for many fields, right? So, right, you can do a really crappy job minimizing a loss plus a regularizer, and you'll still have an outstanding classifier or something like that. And the classifier won't get any better if you were to solve that problem to 8 significant figures. It's the same in control, it's the same in finance, although no one wants to admit it. It's the same in all these fields, right? So, so you could use, so I actually, weirdly, I don't have any problem with somebody using stochastic gradient descent for least squares. It is weird, I agree, but it's okay. Yeah.
So actually, in machine learning, we could argue that we're not actually interested in optimizing the loss function.
You're right.
Because we're actually interested in
Right.
minimizing the generalization loss.
That's right.
So
Yeah, by the way, you may think that's special to machine learning. That's true in every field of applied mathematics. In control, we're not interested in minimizing the least squares thing, 50 steps in the future. We want to save fuel, we want to make it extremely reliable and things like that. That's what we want to do, right? In finance, you don't want to minimize or maximize some stupid quadratic form, which is a fantasy anyway. You want to make money with low risk, right? So in every case, the mathematical formulation is a surrogate for what you really want to do. And then you check it by seeing how it works for real. So statistics and machine learning are no different. Of course you don't want to minimize a loss function plus a regularizer. What you really want, what would really make you happy is if it works under cross-validation. Even happier if you implement it and it's running and it's making good predictions, right? So I agree with you, and that's actually I'm glad you brought that up because it's a very important thing to think about in optimization, which is that optimization is almost always, not always, but almost always, it's a surrogate for what you really want to do, and you should keep that in mind. And yes, in machine learning, you don't want a model that minimizes loss plus regularizer. You want a model that will generalize on tomorrow's data, right? So that's a great point. Okay, I think we'll declare the stopping criteria as satisfied. Good.